Today we'll be discussing about the influence of JRC on the bearing capacity of shallow foundations based on jointed rocks using interface elements. My name is Alwis, and my co-author is Dr. Kurukulasuriya from the Department of Civil Engineering, University of Peradeniya. So the contents of the presentation will have an introduction, the methodology, then the results, and the conclusion and recommendations. So jumping into the problem statement, the failure criteria of jointed rock mass is quite complex, and it depends on the mechanical properties of the intact rock as well as the joint. The effects on, if you place a shallow foundation on this jointed rock mass, and the effects on this due to the undulations of the joints are yet to be studied. And then finite tuning methods have been developed to incorporate interface elements to consider these discontinuities. And the effect from these undulations by using these interface elements have yet to be explored. So considering all this, our study has an aim to understand the effects of joint orientation and joint undulations on the bearing capacity using finite tuning method. The objectives are to use finite tuning method to simulate the different joint conditions, to establish and calibrate the model, numerical model with previous studies, to vary the joint orientation and joint undulation, and evaluate the effects of the bearing capacity. So considering the literature review and highlights, the Moore-Coulomb failure criteria is commonly used, as we know, to simulate geotechnical problems, and especially when it comes to perfectly plastic and elastic perfectly plastic geotechnical materials. Barton and Bendis, however, states that the shear strength of joints are more complex than that, where he has considered this is the Barton-Bendis failure criteria, which was presented by them, and here you can see the sigma n is in equation 1, sigma n is equal to the normal stress, JRC is the joint rock coefficient, JC is the joint capacity strength, and phi r is the joint friction angle. So here you can see these are the undulation profiles, and based on the undulation profiles, there's corresponding joint rock coefficient or the JRC number. And however, due to the limitations of practically using, sometimes not all softwares have these interface elements where you have this nonlinear criteria. So Hoek in 2007 introduced where you can consider an instantaneous friction angle and instantaneous cohesion to convert this nonlinear behavior into a linear sort of Moore-Coulomb behavior. So this is the conversion criteria, as you can see in this graph graphically. So Iman et al., Sutcliffe et al., and Alwis et al. All considered jointed rock masses and how you can simulate them. Iman et al. used discrete element method, while Alwis et al. and Sutcliffe et al. used the finite element method. And Iman et al. considered the upper bound solution. So in the interface elements, zero thickness elements, in the software that we're using, this is Midas SolidWorks finite element software. It's a zero thickness element which has represents the discontinuities between two materials. Alwis et al. Simulated the joints using an equivalent constraint method, and he described the Young's modulus of the joint in the transverse and normal direction as equation 5 and 6. So we are using the same equation to convert to our joints normal stiffness and shear stiffness, as you can see here, and we varied this Rn, I, and RSI coefficient, which is a constant. E is the modulus of velocity of rock, and S is the spacing of the joints. So what we've done here is similar to the study of Iman et al. This study considers orthogonal joint orientation angles of 15, 30, and 45, and these are the constants that we have used, similar to the study which was mentioned before, and the rock mass property as shown here. So by varying this, we have calibrated. We tried. The first step of calibration is done using this condition. This is the upper bound solution, and Iman et al. Showed that his upper bound solution is higher than the lower bound solution, of course. And this is where the study of Alwis et al. Lies. So by changing Rn, I, and RSI to 110 and 100, we've been able to come close to the lower bound solution, but in the 15 degrees angle, it's lower. However, we have selected the Rn is equal to 10, which will be used for the second part of our calibration, which is the use of the dilation angle. And as you can see, the dilation angle, difference between the friction angle and the dilation angle has been increased by 5 degrees up to 30 degrees. in MIDA software, it is generally stated that you have to use the same friction angle and the dilation angle is equal. That means the difference is equal to 0. But by varying this in our calibration, we found out that for the same study, it is coming closer. That is for the 30 degrees and the 50 degrees, it's 13 and 40, 30 and 45. Orientation angle is higher, and it's same when it's 5 minus psi is equal to 15. So here, this is the inequality that we have taken into consideration. That is the friction angle and joint dilation angle. If it's less than or equal to 15, then the dilation angle is equal to considered as 15. And for dilation angle and difference between friction and dilation angle is less than 15, then we have considered it to be the dilation angle to be 0. So then the model setup, as you can see here, the orientation angles that we considered are parallel and orthogonal, 2 joint sets and 1 joint set, which is 0, 15, 30, 45, 90. And for the orthogonal joint sets, the same angles with considering the counterpart of 90 degrees. Mocolum round material was used to represent the joint, the intact mass, and this is the material, the model. You can see the model setup, typical sketch of the model setup. This is the joint, the intact rock mass parameters that we have used. We use the rock type as nice foliate because in Sri Lanka, in Colombo especially, it's very common to have nice type rocks. And this is the JRC numbers that we have selected, 2, 16, 10, 14, and the corresponding coefficient, joint cohesion and joint friction angle that has been obtained by considering Quirk's conversion. For the others, in the equation 1 that I presented, the others are considered to be constants, as you can see, which I have presented here in this slide and is given in the paper corresponding to this. So when it comes to the results, you can see that the one-sided failure mechanism similar to Iman et al. Has been observed for 30, 120, 45, 55, and 135. You can see a similar two-sided failure mechanism. And for 45 degrees, similar to Iman et al. Alpha equals 45 parallel angles, we see the one-sided failure mechanism. Iman et al. Did not consider the angles of 0 and 90 degrees because of the inequality that he has formulated. But we have observed a two-sided failure mechanism when it comes to the jointed rock masses. This is the graphical representation for orthogonal joint sets. And this is the graphical representation for parallel joint sets. If you compare them 1 to 1, the parallel joint sets will show a lower value. That is obvious because more joint sets means more bigger planes. So you can see that throughout these are different orthogonal and parallel joint sets. Only in this case, 30 and 20 is overlap. But in general, we can see 45 degrees angles, orthogonal joint sets are higher than the parallel joint sets. So what we can say is that, of course, this is a very complex phenomenon. That means the joint orientation angle has a significant role in the failure mechanism of joint rock mass and the ultimate bearing capacity, as well as the JRC number has a significant effect on the ultimate bearing capacity. And there is a nonlinear behavior between the ultimate bearing capacity and the JRC number as well as the joint orientation. So further recommendations to this study is that the study was carried out considering conversion of nonlinear failure criteria to linear failure criteria due to the inherent limitation of the software, as I mentioned before. And therefore, for the study, it is recommended to use similar study and carry out considering the nonlinear failure criteria if it is available in the software later, and verify if these same results can be formulated. And the further study would be to investigate on the effects of the rock anchor and the bearing capacity. So these are the references that I have used for the study. So now I will open the floor for questions. Thank you.